Good evening, everyone. Welcome to our next video on apportionment. This next one will start to get into more modern apportionment. And to recap our last video, we looked at Webster's method, which is one of the fairest of all the methods. Um, One of the reasons why it's so fair is because unlike Hamilton's or Jefferson's, it uses zero point 0.5 rounding in order to stay within half of a seat of what the natural quota would otherwise tell us. Um, Now, obviously, it will either tend to go up or down from that, but the initial value at least is within zero point 0.5, whereas Hamilton's and Jefferson's can differ by as much as 1. And they certainly had their own issues, Hamilton's method being unconstitutional, and Jefferson's method clearly favoring large states. Turns out Hamilton's method does favor large states as well, but not as badly as Jefferson's does. Okay, and we settled on Webster's method as being really fair because you round everything to 0.5 and it keeps the numbers as close to the natural quota as possible. The divisor that comes up is generally considered to be the closest to the original natural divisor that you do when you first start the problem. So that's all wonderful, right? Except that because of that, well, not because of that, but tongue-in-cheek perhaps, it was used exactly once before being thrown out. Okay, so at this point, there's a little bit of a story that I'd like to tell. It's a fairly lengthy story, but because I have the time in the video, I'm going to tell this whole story. And of everything that happens from the time that Webster's method gets implemented in 1840. And the story covers all the way through 1900, and then the second part of the story, which is actually stuff that is more pertinent to the class, certainly from 1900 to 1940. Um, and then the new apportionment method that we're going to learn picks up in 1940. So I've got about 100 years worth of story to tell. Feel free to skip this part of the video. I'll have a chapter set up um, so that it'll mark off where the stuff that is a little, not, I guess, not more important, but because it's all important, but the stuff that's a little bit more pertinent to the actual rules of apportionment, we're going to pick up later. But this story is just too good to not tell of everything that happens between 1840 and 1900. Um, because it kind of goes to show how just one little change or one little decision uh, can make such a huge historical impact. Um, okay, so feel free to skip ahead if you don't need to know the story or if perhaps you've heard some of it in class and are just here just to review some of the basic concepts. I'll put a chapter in for that. Okay, so here's the story. In 1840, Webster's method is put into place by Senator Daniel Webster. It's used once, and Congress likes it. So all is well and good, right? Well, in 1850, another representative, Samuel F. Vinton, he's a Whig from Ohio, um, he comes up with a novel approach as they're getting ready to apportion. And remember that back then, they have to debate that. According to the laws of the Constitution, they essentially have to debate this every 10 years. Um, Even though they like Webster's method, and it's generally a good method, um, according to the rules that they had at the time, they do have to debate this every 10 years. So it opens up the door for stuff like this. Samuel Vinton comes up with a novel approach to apportionment. He says, hey, why can't we just divide everything out um, and give all the extra seats and round up only those seats that have the highest unrepresented populations? Now, you and I are going to look at that and do it. Dr. Picard here tells just, oh my God, really? Really? Do you not know your history? Seriously. So first I want to shake my head and say, no, Hamilton did that like 75 years ago. Hello. But, plot twist, Congress approves of this. Because of course they did. Well, I mean, Hamilton had at this point been dead for 50 years. Yes, his wife was actually still alive at this point, amazingly enough. Um, so, but yet, she's focused on other things at this point, and she's well into her 90s at this point. Um, so she can't really kind of say, "Hey, listen, look, we tried that once already." Um, but Congress does approve of this, and so in 1850 we go back to Hamilton's method, um, which now you're starting to wonder, wait a second, how could we? Wasn't it voted unconstitutional? Well, here's the thing. As we now look at I'll pull up the rest of this here. Um, yeah, I know. They now call this the Hamilton-Vinton method of apportionment, simply because they both developed it independently of one another. Different times, Vinton had no idea that Hamilton had already done this. Okay. Um, so anyway, the original supposition for why Hamilton's method didn't work was because of the 30,000 rule. Was the 1 in 30,000, and the 1 in 30,000 rule was a little bit too close. Like when Hamilton created his numbers, he originally had a house size of 120, if you remember, back in the 1790s. And that didn't work because when some states rounded up, it dropped their representation. And it was very, very clear. Like Vermont had 85,000 people, but 3 representatives. And that did not work in the Constitution. So since then, though, we're now almost 100 years later, as the population has grown, the amount of people in the House has also grown. But um, because they've gone up together, the amount of people per representative also will increase, not as strong as if um, the number of people in the House would remain constant like today, but um, certainly it was a balance. And the founding fathers, if you remember, they didn't want there to be too many representatives in order to either dilute the pool or um, not, or to like put too much faith in just that giant body of representatives. But they also didn't want the representative body to represent too many people because they didn't want to lessen the power of each particular voter and that person as a constituent of that district, right? So they wanted people to feel like they had adequate say with their representative. Um, so it was a careful balance. And so now this number is much higher. So it's like, 1 in 70,000, something like that. It's a lot higher number. Um, so maybe 1 in 50,000, 1 in 60,000. It's in that range somewhere. And I can actually look it up, but I haven't yet. So that argument is completely moot. So Hamilton's method completely works, and so they use it. Now, a side note, and I'll mention this a bit later on as well, not for nothing here, because Congress does at least recognize that Webster's method is good, and they're getting rid of something that not for any particular reason. Like Jefferson's method, Hamilton's method the first time, like they dropped those methods because there was clearly a problem with that. Um, they're dropping Webster's method not for a problem, but because they just happen to settle on something else. So, um, what they decide to do instead is they decide that whatever they do, Hamilton's and Webster's must agree. And so going forward, starting in 1850, um, they choose a house size based on the census. They then choose a house size such that Hamilton's method and Webster's method both agree on the number for each state. So really, it's as if they're both in play. And in that case, you can make the case that like that's actually gives it an extra strong, sort of validity because you have a rounding method and a divisor method that are both agreeing. And you may think like, oh, that's got to be pretty hard to do. It turns out it's not. These two agree a fair often amount of the time. Um, they're going to most likely agree um, when there's very little extra seats award. Okay, okay, so based on everything's fine, right? Until 1870. And so here's our first little little intrigue in the story. The illegal apportionment. Okay, so the 1870 census happens. Now, mind you, the U.S. government is extremely lucky here because the Civil War fits entirely within the scope of the 1860s, right? So when the 1860 census is done, the states are still a part of the United States. I think possibly only South Carolina has seceded at that point by the time the 1860 census happened. Um, and they still essentially counted it. And but most of it was still together. And so they had a pretty normal census despite the Civil War about ready to start. And by 1870, and they did the apportionment in the 1862. Um, they, even though by then the Civil War was raging on, um, the government and the House of Representatives itself as a legislative body um, did not or was told you whatever way you want to think about it, whether Lincoln told Congress to kind of pretend like it was whole, which makes sense. And so Congress apportioned in 1862 as if all those states were still part of the Union because according to Abraham Lincoln, they were. Like the secession was unconstitutional. Civil War was going on to account for that. And Congress said, well, if they come back, if their representatives ever want to come back to Washington, we'll have seats for them. And we'll pretend like everything's back to normal. So Congress, it was certainly in its best interest to do a full apportionment with all the states. Um, by 1870, Civil War was over. The states started to rejoin the Union, um, and now Reconstruction was happening. So Congress was set to carry out a Hamilton apportionment in 1872, again under the guise that Hamilton and Webster's method would both agree. But then something interesting happened. A supplemental bill on May 30th of 1872 was passed in Congress. Prior to then, they had already agreed on an apportionment size of 283. Um, and that was all fine. But then, just out of nowhere, on May 30th, 1872, they passed a supplemental bill, and you can actually read this in the it's in the statutes at large, um, which is kind of interesting to see. And they say, out in the bill, it says after the apportionment is taken from the 1870 census, they call it the ninth census because it's the ninth census of the country that's taken. Um, and after the apportionment has been done, then the following 9 states are going to get one extra seat beyond that for the duration of this cycle. And those states are New Hampshire, Vermont, New York, Pennsylvania, Indiana, Tennessee, Louisiana, Alabama, and Florida. Um, Now, I tried a bunch of research on this, and for the life of me, I can't seem to figure out why they did this. I can't find any documentation anywhere to ask why. And you know, that would be a question for like the Library of Congress or something. So, um, Tell you what, if I ever make it to Washington, D.C. again, um, I'll actually go there and ask this question. So anyway, but those 9 states, because I looked through the apportionment tables for both 1860 and 1870 and wondered, like, did those 9 states lose a seat, or were they threatened to lose a seat? Not that I can be aware of. Um, the only thing I can think of as a possibility for doing this was that given the census numbers, perhaps they couldn't get Webster's and Hamilton's to agree with one another, and those were the states that it was off by. Um, that could very well be. And then what they decided to do was give those 9 states to um, allow for the methods to agree without anybody losing a seat. And that could very well be something like that, right? Um, and it turns out, like, you may think, like, oh, is this unconstitutional? And the answer is no. It says says, um, Congress has to reapportion according to the respective numbers. Um, the 14th Amendment, you know, basically kind of updates that a little bit, just in terms of, counting everybody. And but it never mentions that Congress can't pass further laws. But Congress was apportioned, like the House was apportioned properly according to the Constitution. So this is perfectly fine. And this provision does allow Congress to make laws on this. So this is all fine. And it's not the first time this has happened either. Um, there have been other times, like where in particular, I think in 18, I want to say 1850, the 1850 apportionment, California had just become a state, and they were to have either 3 or 2 representatives. They were promised, it was something like that. They were promised a certain number, but when they did the apportionment, they were one short, and so they just gave California an extra seat um, to appease them. Like that sort of stuff turns out has happened a couple times. Okay, but here's the issue: if you were to actually compare with the true reapportionment using Hamilton's method, um, the complete list of the 292 that was officially installed starting in March of 1873, inauguration day is when all the new elected officials coming in. Um, 2 seats that should be in New York and Illinois were instead in New Hampshire and Florida. So it's interesting to consider that maybe there is a reason for this, because it turns out Illinois, in this difference between 1860 and 1870, Illinois picks up 5 seats, not including this one that they lose in this reason. So really, they were picking up 6 seats, um, and this made them only pick up 5 seats. And New York, I think, was picking up 3 in this exchange. So I wonder if that had something to do with it. But anyway, so there are 2 seats different from a true apportionment. New Hampshire and Florida picked up extra seats, right? Okay. I mean, it's 2 seats in 300. Does that really matter? Oh, oh, this better not matter. Oh, but it does. You poor naive soul. If you think that those 2 seats, I mean, seriously, New Hampshire, of all states, no offense to New Hampshire, but it's so tiny and just there. Like, New Hampshire really hasn't been a deciding factor in much, right? I mean, yeah, they get the first votes in the presidential election, but other than that, oh, but watch. 1876 presidential election happens. So Rutherford B. Hayes, the Republican, versus Samuel Tilden, the Democrat. Um, Obviously, now we're still in the 1870s, so Congress and therefore the Electoral College is apportioned according to what happened in 1870. Now, Samuel Tilden was a pretty popular fellow. He had not just the lead in the popular vote, he had a majority. Um, when the first vote count came around, Tilden was leading the electoral count by the count as you see here, 184 to 165. Four states were unresolved, with a grand total of 20 electoral votes. And yes, in case you're wondering, yes, those two currently differ by 19. You can probably see where this is going. Okay, so right there, I mean, Samuel Tilden has a majority, right? Easy peasy. But those last four states, they have some issues, some major issues. And you think the 2020 election had issues. Okay, so here's what happened. There are four states that did not return results: Florida, Louisiana, South Carolina, Oregon. So three southern states, but then one northern state too. Okay. So in Florida, Louisiana, and South Carolina, they all had a similar issue. All three reported Tilden as the winner, um, but there were a lot of allegations of reports of voter fraud, intimidation towards Republican voters. Um, Remember back then that the Democrat Party was like the Southern Democrat Party. They were the pro-slavery party, um, and they were made up of, had a lot of wealthy plantation owners and things like that. So this was like the Southern Democrat Party, right? And they all reported Tilden as the winner. Yet, I mean, just in South Carolina, it is said that 150 black Republicans were murdered um, at the polls or for voting Republican. That kind of stuff was happening. South Carolina, in particular, another thing is the number of ballots counted was 101% of the total number of possible registered voters in the state. So, um, like, in other words, like 101% of like the entire voting age population. So that is that's a lot. And like they already had access. They knew how many voting age people there were in the state, um, because they just took a census, right? And they had just taken a census like 6 years ago. And so South Carolina tried to pass this off as like, oh, well, a lot of people just, you know, becoming of age to vote, things like that. Hmm. Okay. But yeah, the numbers just doesn't work. Now, what further complicated matters with these three states is the acting governors took it upon themselves to disqualify these results. Um, so at this point in time, again, the South is still recovering from the Civil War, and one of the things is the whole idea of Reconstruction. And part of that was the federal government occupied the southern states, and there were federal troops, like from the north, they were in the South, and they were helping to, control a lot of different things, right? And one of the things that the government did is they installed governors into all seven of the seceding states. They installed federal government leaning Republican um, governors in those states, in order to prevent them from any sort of bias, right? Because remember, there's a lot of laws that Congress can't touch, and that whole, things that are not explicitly given to Congress is the domain of the states, and especially because states were really big on the states' rights, so they wanted to make sure that the states were doing things as they should, and so these Republican governors were in these very clearly Democrat-leaning states, or at least in terms of voting, right? So they decide to disqualify the results and sign the Republican certificates. Remember that the governor has, when he receives the results from the state and receives the votes of the electors, um, he he has to choose. whether to accept Republican results or Democrat results. And he signs the Republican certificates. All three of these states, same thing plays out. And when he signs the Republican certificates, he then assigns Republican electors from those states. Um, okay, so there's a problem right there because we don't even know if the governors even have the power to do that. In um, Oregon was kind of the opposite. So they clearly favor Rutherford B. Hayes. The general population does, but the governor's Democratic, so it's the opposite situation. Um, and just showing that politics sometimes there's no bad, no good. So the Democratic governor disqualifies one of the three Republican electors um, because he's an elected official. Article 1, Section 1, sorry, Article 2, Section 1, Clause 2 of the Constitution states that no elector for the Electoral College can be a person who holds public office um, because they don't want that person to be partisan. Electors have to be nonpartisan, and that's because they have to vote for whichever candidate. They're generally bound by whichever candidate wins the popular vote in that state. And then there's a whole thing with faithless electors, blah, blah, blah. We're not going to get into that, though. So he disqualifies and dismisses one of the Republican electors and replaces him with a Democrat, one who would vote for the Democratic candidate. Can he do that? Yes, he can. Um, and that's actually within his power to do. The problem was that the man in question wasn't actually an elected official. He was a former elected official. He was the former postmaster of the state of Oregon. And the law says no person who holds, or what they call, I forget what the term they use in the Constitution, who holds a trust, um, an office of trust or something like that. So, in other words, any elected official. So he's a former elected official. The Constitution doesn't bar that because he's not currently an official. And so people squawk about that too. And so two separate sets are set. The governor sends two Republican electors and one Democrat, but the Electoral Commission for the state of Oregon tries to override him and send in three Republican votes as they should. Okay, so this became a giant mess. A lot of meetings, committees, crisis is starting to brew. In February of 1877, there's no resolution. Inauguration is less than a month away. Back then it was in March, not January. If it were in January, he'd be in a lot of trouble. Um, Eventually, they decide to settle this. Five senators, five representatives, five Supreme Court justices. So like all three major bodies come together. Only the executive branch stays out of this one. And they all come together in a special electoral commission to untangle this mess. And after a lot of discussions, in a series of 8 to 7 votes, a deal is brokered. All four states would give up all objections and certify the Republican candidate Hayes. In return, if Hayes gets into office, he would promise to remove all remaining federal troops from the South and end Reconstruction. Um, that's huge. Um, and that's a heck of a deal. Now, Tilden, for his part, being the Southern Democrat, um, he probably would have removed it too, but the government was not going to put a Democrat in the White House, not at this point. Um, and the states, by their own admission, definitely had these problems, right? So they decide to go this route, and it's close. It's a series of 8 to 7 votes. but the South reluctantly agrees to this deal, and Hayes is elected. 185 to 184, the smallest margin of victory ever. Um, and Hayes is a man of his word, and he pulls all the troops from the South. Um, some say like it was too quick and he should have waited, um, but no, this is what happens, and this is part of what's known as the Compromise of 1877. Okay, fascinating story, right? Okay, um, great, that's wonderful. So that's kind of the side piece to all of this, and but there's one more thing though, right? How does this affect apportionment? Because I've gone off on all this election stuff, right? And that's all well and good. But remember, this is about apportionment. Now, here's the thing. Remember I said before that that apportionment was slightly off? New York went to Tilden. So New York, their electoral votes went to Tilden, but Illinois, New Hampshire, and Florida, all three of those states voted for Hayes. So that's an issue because if New York had its extra seat that Hamilton's method would grant, so remember that New York and Illinois were due an extra seat but never got them because of this deal, right? So if New Hampshire and Florida never had those votes, Tilden would have had an extra vote coming from New York, and he would have had um, a 21 vote lead rather than a 19 vote lead because instead of having, um, so like the New Hampshire vote would have gone to Illinois, let's say, and that would have been fine. Like that would have been Hayes for Hayes, and that wouldn't change anything. But the Florida vote, if that seat had gone to New York, that Hayes vote would have turned into a Tilden vote, and so that would have given Tilden a 21 vote lead, and all of the discussions, everything would have been completely irrelevant because the disputes only added up to 20 seats. Um, so Tilden would very likely have been president. Now, would they still have had to untangle that mess? Yes. Um, and scholars could even make the case that they could have dove in deeper and found more um, fraudulent things from that election and found more discrepancies. And so maybe all of this would have still happened. We don't know. Um, but the moral of the story is that just those little decisions, every decision you make, even if it's one seat here, one seat there, like, they all have a major impact on how history plays out. What was that line from Hamilton? History has its eyes on you. It's very, very useful here. Okay, so that's really the end of the story part. Just add that little epilogue on there. Um, so now let's look at what this means about like getting back to actual apportionment and how we go forward from here. Okay, so the next thing that we have to look at now is 1880. Okay, um, so at this point, as I said before, um, Congress did see the fairness of Webster's method. Um, Jefferson's method was out. Hamilton's method still works. At last, common sense prevails. Finally. Okay, so let's go on to 1880 now. Because, of course, we can't have a single census go by without something happening, right? So chief clerk of the Census Bureau gets all the census data, and then he gets the data, he parses it, and then he has to create the apportionments. He sends it to Congress. Congress approves it, sends it back to the Census Bureau. He makes a note of it, and then according to current law, by I want to say January 25th of the 1 year, possibly the 2 year, um, by January 25th, they have to notify the states of how many representatives that they get. And we knew pretty early on for 2020. Um, so I want to say by early 2021 it was figured out. So same thing here. So like by January of 1881, the states have to be notified so that they can start doing the redistricting process if they need to. So the chief clerk, in preparation for doing all that, he creates a Hamilton apportionment for every single house size from 275 to 350. He also does a Webster apportionment. Congress always asks for that so that they can make sure that Hamilton and Webster's match. But the chief clerk noticed something really strange. When he did the apportionment at 299, Alabama was awarded 8 seats. Great. He then did the apportionment at 300, but when he did that, Alabama only got 7 seats. Well, that's strange. They went up. How could it be that if you go up by one and the total house size 300, you're adding a seat? So why would Alabama have one taken away? And he redid this math and it was legit. Like, this was correct. This was the correct result. So the heck? Like, okay, really, Congress is trying to be reasonable now. Forget the other stuff, the bickering, whatnot. Trying to be reasonable. The math just won't let them. Lovely, huh? So what's going on? This is actually an easier thing to explain than you think. Okay, so let's take a look at an example here. Um, and so this one here, I actually get to do a little bit of writing now, right? Okay, um, so let's look at this here. So let's say we have 3 states. We have an A, B, and C, and we have a population of 6, 6, and 2. Okay? Let's apportion it with 10 seats. Let's create a 10-seat, um, 10 seats little body, right? Council. And so the fair share, this is the natural divisor. Um, Keep in mind that with 10 seats, the state population is 14, so the divisor is going to equal 1.4, right? So 6 divided by 1.4 is this. 2 divided by 1.4 is this. Okay, no big deal, right? And according to Hamilton, you get a 4, a 4, a 1. Because they've got the higher decimal, they get the plus 1. Okay, now let's do the same thing again, but this time let's do it with 11 seats. Okay, and when you do it with 11 seats, now you're going to have a population of 14 divided by 11. Okay, and so now your divisor is 1.27 repeated. Okay, um, so D equals 1.2727. So that's your new divisor for 11 seats. Notice what happens. 442, okay, fair share 441. There's 2 seats remaining, not just one, because there are 11 seats. It makes sense that we're going to now have 2 seats to assign rather than one. Look at the decimals. A and B have the same population, so their decimals grow together. Their decimals go up, zero point 0.2 to zero point 0.7, zero point 0.2 to zero point 0.7, and then C's only grows 1.4 to 1.5. They only grow by a tenth versus these larger seeds, which are growing by zero point 0.5, zero point 0.4 at least. This is why Hamilton's method favors large states. It's a little bit more insidious to see, but this is a pretty good explanation of it. Now, here's what's more important. What happens here is those 2 extra seats, because A and B both have the same population, they take both of the extra seats. And C no longer picks up the extra seat that it has here. So the idea is not that, so the way to think about this as a apportionment paradox, C isn't actually dropping a seat. They're just suddenly failing to get a round up value. They're due 1 seat. The second seat that they had was a freebie for round because they had the high decimal and they could round up. But at 11 seats, they're no longer the highest decimal, so they no longer round up. This is what happened to Alabama. They were actually due 7 seats, but at 299, they picked up an eighth seat because of the way the decimals lined up. But by 300, their decimal didn't quite grow as far. They only keep the 7. So this, as you can tell, is probably going to happen a fair amount, right? So Congress's response to this, when they, so the chief clerk shows them this, and Congress is like, okay, can we just avoid that? The House size was set to 325. Alabama got its 8 seats. Um, Congress just was going by the thing, and apparently they knew of this. Um, so when the chief clerk was like, "Holy crap, what's happening here?" Congress was kind of like, "Yeah. We're just going to choose a size so that nobody loses a seat. We got this." And so it's kind of like they knew what to do. Um, in 1900, it happened again, but this time to 5 different states. And then here's something. Um, so Colorado was due 3 seats. Um, Colorado, kind of an odd, really extreme case of this. So Colorado was due 3 seats, and at every house size possible, they were due exactly 3 seats, except if the house size were 357. Um, if the house size were exactly 357, they'd own the decimals would line up in just such a right way that they'd only get 2 instead of 3. Now, it just so happens at this time, as a stroke of luck-ish, the chair of the House Select Committee that oversees the process of apportionment every 10 years um, was a politician who hated Colorado, and he butted heads with Colorado's legislature and the governor. I don't remember if he was from Colorado and had this issue, or he just like always butted heads with their Colorado's representatives and governor and whatever. But he's in power. So, of course, he recommends a house size of 357. Um, Thankfully, though, he was overruled. Congress was like, no, you can't do that. So the house size was instead set to 386. Damage was done, and they realized that Hamilton's method had to go because this was just going to keep happening. And mathematicians, which are getting better and better at working with this stuff, um, they realize that Webster's method is not going to do this and cannot do this. So wonderful. Back to Webster's method. So in 1910, um, they decide that Hamilton's method's gone for good, and it's back to Webster's method. Oh, wait, fair. Congress doesn't really like fair, right? I know that's the running joke, but really it's just bad timing. Okay? So Webster's method is used in 1910. But a problem was starting to happen so at this point, so 1910 happens, the apportionment, which was set in 1911, the house size is set at 435. And if you recognize that number of 435 seats, that's the current number of seats that are in the House now. So in 1920, the debate was extremely divided, and for several reasons. Mostly being the fact that they were trying to keep this balance between number of representatives and representation in, at the person level, at the population level. The problem, though, is that they kept trying to recommend a House size of 483. The room in Congress was full. 435 seats plus extras for staff and territories um, for non-voting like representatives, um, they were out of room. And so there was a lot of back and forth as to whether they should cap the number or like they can't cap the number because that's just gonna, make the votes count less. And so it went back and forth. It was so divided that for the first time ever, no new apportionment was created, despite the constitutional need for it. Um, that's huge because like that this had never been done before. Now here's the thing. You don't go against the Constitution ever. There is no getting around the Constitution. Um, so when it says that they have to figure out apportionment every 10 years, okay? Um, it says the case piece of the Constitution says, um, in such a manner as Congress, they shall by law direct, meaning that they have to do an apportionment every 10 years, but they can decide for themselves how they want to do it. So 1920, nothing happens. And they keep talking it up, and nothing ever comes of it. 1923 passes, 1924 passes, like nothing. Not even the Civil War could stop this. And nope, they just can't agree. So what eventually happens? Um, so in 1928, I don't know if it's listed here. Yes, okay. So in 1928, Congress passes a law retroactively okaying this. And so they realize that they have to do something. And the Supreme Court is kind of telling them, like, look, guys, it says to the Constitution, you got to address this. And Congress says, okay, here's the thing. Um, why don't we have to address 1920? And so the law says that in 1920, says that apportionment will stay the same as the numbers from 1910. That satisfies the Supreme Court because, according to the Constitution, they have to address it, and they did, even if it's not using the current census numbers. And so Congress says, well, Constitution doesn't say you have to do the current census numbers. So the fact that Congress made a law that says that we're going to keep with what we had in 1910 is totally fine. And so then Congress then adds to that and says, okay, then how about we just say this? And let's just say that we're going to leave this to rest. And every time a census happens, if Congress does not specifically change the law or wish to change how things get apportioned, the House automatically apportions itself based on the last known parameters with the current census data. So Congress finally, after all this time, smartens up and says, passes a law that just says, once we pick a method, it's just going to reapportion every 10 years unless we feel like changing it. So the first test of that happened in 1930. They're still discussing this, by the way, but in 1930, no new discussions, no new methods coming up with, so the House was automatically reapportioned using Webster's method. Um, and the reason why they were able to finally set this was because the House size, as part of this bill, was set to 435 for good. Um, Congress quickly realized that they're just, no matter what they try to do, 435 was it. Unless they tried adding on to the Capitol, which wasn't going to happen either. They can't build it. I'm like, oh, let's build a new Capitol. And everyone's like, no, can't do that. Okay. Um, but by at the same time, some Harvard mathematicians came up with a new method. Um, and they had presented it to Congress, and they were arguing about this in the same time around 1930. Um, this method is agreed with Webster's method in 1930. So the data was exactly the same when they did the calculation. But by 1940, the two methods differed, and they produced different results at 435. So it's just lucky that it worked in 1930. So they just stuck with Webster's method. By 1940, now it's time to choose. So let's see what it looks like. This method is called the Hill-Huntington method. Sometimes it's called the Huntington-Hill method. Depends how you want to write. Okay, so the premise of this method is seeking to normalize the effective representation rate between the states. So Webster's method, what it does is it makes as small as possible the arithmetic distance to the quota. So like by by rounding everything to zero point 0.5, you're always within zero point 0.5. The initial value is always within zero point 0.5 of the natural quota, right? And that's all fine. Um, Instead of rounding to zero point 0.5, though, this Harvard mathematician decides to say, hey, listen, let's round up the geometric mean of the fair share of seats, or the natural quota, if you will. Okay, how many of you have heard of a geometric mean? Maybe, maybe not. Let's find out. Okay, so what is it? Okay, so the geometric mean, okay, is, so let's kind of explain this a little bit here before I jump into that part here. So for Webster's method, okay, oops, oh dear, change things, oh, cancel. No, don't want to do that. All right, so, uh, so Webster's method, so you find the arithmetic mean. And the reason why we can call it the arithmetic mean is because like when you take two quota values, right? So if you have, say, um, say you have a natural quota of 5.235, let's say, okay? And so 5 plus 6 divided by 2 is 5.5. So the rounding is like because it's in between 5 and 6 seats. So the natural quota being this, they're going to get either 5 seats or 6 seats. Um, and so the average between 5 and 6 is 5.5. Now, this means that we have to decide which way to go. Okay, so is 5 closer to this, or is this closer to 5 or closer to 6? And so the difference here is at 5.5. If this number is less than 5.5, we go down, and so this would go down to 5. And if this is higher than 5.5, it goes up. And that keeps the distance to the natural quota as small as possible. But for Hill-Huntington's, he uses the geometric mean. And the geometric mean, let's use the same natural quota of 5.235, right? So the geometric mean is to multiply 5 by 6. Again, either they're going to get 5 seats or 6 seats and take the square root. And this is the square root of 30, which is a little bit less than 5.5. I don't have, hold on, let me find a calculator here. Grab my phone, calculator, turn it this way. Oh, look, square root button. Oops, I forget. This calculator, I can do it the other way. Root 30, 5.477. Okay, so why do this and what's the difference? The difference is this point is the point between which you have equal proportions between 5 and 6. So in other words, if you have a number line here, okay? So let's look it up here. Let's do the same thing here. Say you have a number line, and it goes from 5 to 6, okay? And we choose 5.5 in the middle because 5.5, that's the average distance. It's the point by which the distance to 5 and the distance to 6 is the same. Let's do the same thing here. It's a little bit less, 477. So what's the purpose of that point? The purpose of this point is the ratio of growth. 5.477 divided by 5 is approximately equal to 6 divided by 5.477. And you can show that that's actually true. Um, and as you can see, if you think about cross multiplying these fractions, um, you get this squared equals 6 times 5. And so you can kind of see where you get this number 5, but from taking 6 times 5 and then doing the square root. But what this does is it equalizes the proportion here and here. And so these people are like, listen, isn't that what Thomas Jefferson wanted in the first place? Was when he said, according to their respective numbers, he wanted the effective representation by the representatives to be as close as possible to each other among all the 50 states. So we want, Montana's level of representation to be the same as Connecticut's, to be the same as Arizona's, to be the same as Alaska's, and so on and so forth, as close as possible. Um, and they decided this is the number that's going to do it. And so here's how this works. Instead of rounding at 0.5, like instead of going like, if the natural quota is on this side of 0.5, you go to 6. And if it's on this side, you go to 5. The same thing's going to happen here, but the dividing line is 5.477. So if it's above this value, if it's on this side of the mean, you go to 6. And if it's on this side, you go to 5. Now you may wonder, how different would this really be if the rounding value is either 5.5, 5.477? Could that really be that different? The answer is, for small situations, no. In most smaller situations, like the ones we do in class where we portion 4 or 5 things, these two are going to agree most of the time. But when you get to the case of 51 entities of the United States, then you've got a situation um, where the differences between the quotas are so fine and so precise that this does produce a difference. So let's see how this works. Okay, so this is very similar to Webster's method, but the calculation is just a little bit tougher, and you're going to have to do one extra bit. So you calculate the natural quota, fair share, right? The next thing you do is you find the geometric mean of the two whole numbers that the natural quota sits between. Okay? Remember, the natural quota is, say, 8.3375, then they should only get 8 seats or 9 seats. So what we do is we find the geometric mean between 8 and 9. 8 times 9, take the square root. That's 8.4853. Again, close to 0.5, but a little bit less. That's where we're going to use rounding. If the natural quota is on the lower side of this number, you go to 8. And if it's on the upper side of this number, you go to 9. So, for example, if you have a natural quota of 8.3, you'd start with 8 seats. And if you have a natural quota of 8.49, you'd start with 9 seats. Okay. The rest of it afterwards is exactly the same as Webster's. Find a divisor such that when all of the above is performed, the correct number of seats is allocated. That means in order to do the breakpoints, you are going to have to use the geometric mean again. Okay, so here's the formulas. Pretty self-explanatory, very similar to Webster's method, but because, again, we're dealing with the breakpoint at a square root, so the geometric mean, we will have to build that into our breakpoint calculations. Okay, let's just go ahead and do one out. As usual, just like Webster's method, you may have to add seats and you may have to subtract seats. Okay, here we go. So we have six areas, and we need to do an apportionment of um, using Hill-Huntington method, and we're going to create a council to represent the sizes of these departments. Let's say this is the number of employees in each place. So I guess the question is, what would be a good number for your council? You know what? We could really do just about anything. So I'm just going to pick a number, and let's say D equals, I'm just going to go with 44. I don't know why, I just like the number 44. Okay, so let's do all this out. Let's add this up. Okay. Right. So I have this just recording a screen, so my calculator is going to be off the side here. Um, that's fine. 97 plus 196 plus 26 plus 1125 plus 58 plus 142, 1644. Okay, 1644 divided by 44 equals 37.36. Repeated. Let's just go with it. Again, I have no idea what's going to happen here, so we're just going to run with it. Okay? Okay, so the first thing is let's create our natural quotas. So let's do 97 divided by 37.36, and we get 2.5961. Okay? And then we're just going to do the same for all the other ones. 196 divided by, okay, 5.2457. Okay. Um, 26 divided by 37. Okay. 0.6959. Okay. And I'm going to take these numbers and I'm going to scoot them over. And so these will be the natural quotas. Okay, let's keep going. 1125 divided by 37.36. 30.1095. And 58 divided by 1.5523. And 142 divided by 3.8005. Okay, so that's going to work here. So 2 and 5 is 7, 37, 38, 39, 40, 41. So if this were Hamilton's method, we would have to award, um, we'd have to award 3 extra seats. Okay. All right, so let's take a look what's happening here. So we are going to round. So here's the one thing that's going to make this a little bit easier, right? So um, let me change colors here, and then let's do some square root calculations, just so you get some idea, right? Okay, so we're going to do the square root to do the geometric mean. So we want to find the geometric mean of the two numbers that this could potentially be. So it's either going to be 2 or 3. You're either going to get 2 or 3 seats. And so the square root of 2 times 3, well, that's the square root of 6, right? So let's do that. So we'll do root 6, and that's 2.4495. Okay, so 2.4495. All right, let's do the next one. Square root 5 times 6. And we kind of did that one, but let's just kind of repeat that one. 5.4772. You might notice that these all have a 4, 4447. That is by design. 0.6959. Okay, so what's the square root of 0 times 1? 0. Now here's an interesting situation. What this means is as long as the natural quota is higher than 0, it will round up. And so what this is going to happen is they are going to auto gain a seat. But not because we specifically added to them, but because the Hill-Huntington method just naturally does that. Lowndes' method does the same thing, um, where any entities that do not um, get representation from their natural quota automatically gain one in the process. Because this is specifically coded in the Constitution that everybody gets one, this makes Congress very happy that they don't have to do it. Just the method works automatically. All right, so let's do some of the other ones. All right, and we just continue here. So 30 times 31. Okay, because this one there's a lot of seats, right? 30 times 31 is what, 930. And you get 4930.4959. 1 times 2, that's the square root of 2. And then the square root of 3 times 4, so the square root of 12. 3.4641. Okay, this is a point. It's going to make it a lot easier. Notice my geometric means are always zero point 0.4, with the exception of the 0. What that means is, except for the ones that you got the 0, any other one, as long as if the quota, natural quota is above 1, then you really only need to do this part if you've got a natural quota that's a 0.4. Like if it's got like 2.4 or 5.4, then you should do this. Other than that, the rounding rules are going to be exactly the same as what you already know. So any number that's above 0.5 is definitely going to round up. So we're going to start with 3 seats. Anything that's below 0.4 is automatically going to round down. 0 is the exception to that. But they're going to get 5 to start. They're going to start with 1. They're going to start with 30. They're going to start with 2. And they're going to start with 4. And that's because all of these values, this one, they're higher than this, which we knew automatically by the fact that they're above 0.5. So let's add this up. And I get 8, 9, 39, 40, 41, 40, 43, 44, 45. Okay, so we get 45. Good. For a moment, I was worried that we were going to hit it spot on and we wouldn't be able to do all the breakpoint work. Okay, so here's my initial values. Okay, so now what we have to do is we need breakpoints. So do we have to gain seats or lose seats? D is 44. Well, sorry, I should say S is 44 here. House size is 44. So we have to go down one. And so when I do the breakpoint calculation, I'm going to do the population divided by the square root of this times the number below. And so I want to know where the geometric mean is between 2 and 3. So for this, I'll just turn on the calculator, and I'll switch to a different color. Switch to purple. So the calculation I'm going to do here is 97 divided by square root of 3 times 2. So it's the square root of the apportioned number times 1 less. So 97 divided by root 6. Uh, 6. 39.6. So about 39.6. So this is going to be my breakpoint divisor. Okay, next one, 196. 196 divided by the square root of 5 times 4. And I'm doing this because I have to lose a c. 43.826. Okay, so what's happening basically, my divisor is sitting at 37 and it has to go up a bit to get the number of seats to drop by 1. Okay, for this one here, you're dividing, so your divisor here, you're going to have 0.26 divided by the square root of 1 times 0. We know that's 0, and you get division by 0. So for this one, I'm just going to put auto, because they're automatically going to gain a representative because of the square root of 0. Okay. Let's do more. Okay. So 30 times 31, that is 930. And so we do 1125. Let's clear my calculator out. 1125 divided by the square root of 930. 36.8902. Hmm. For a moment, something didn't look right. Sorry about that. 30, what's the number again? 36.89. Which I find interesting because that's less than a divisor. Hmm. I don't know. I'll have to look into that. Let's do the same for the others. Oh, you know why? Because I went up, not down. All right. So I just realized that's a mistake. Let's backtrack that there. I did 30 times 31. I should have done 30 times 29. Okay. So 30 times 29 is 870. So we're going to do delete, delete, we're going to do 870. 38.1411. Perfect. Okay, public relations. Let's do that one too. 870, or sorry, 58 divided by root of 2 times 1. So square root of 2. 41.0122. And then finally, 142 divided by square root. Now the assigned 4, and we want to go down one, so 4 to 3, so square root of 12. 40.9919. Okay, so the ones closest to the, except for the automatic ones, right? Except for the automatic one, so they pick up. Um, hmm. So we don't worry about them. So the key here, the thing about the auto, right, is they're actually the farthest away from the divisor because if you were to divide by zero, you get really infinity. So what that's going to show you is that they never actually lose their seat um, based on this method, and that's good. All right, so who is going to be the first to lose a seat? Remember, the divisor has to go up. The divisor goes up from 37, and the first number it's going to hit is 38. First number it's going to hit is 38, and so we're going to go down to 29. Okay, now okay, so it's the smallest. So now that's going to be the first one to lose a seat, and we only need to lose one, right? So as before, we want to make sure that we go past one, but not as far as the second divisor. The second divisor is up here, 39.6. So 39.6. So we have to choose a divisor that's in between 38, 39. Let's just do 39. So new divisor. So here's my apportionment. And where's my pen? Here's my final apportionment. 3, 5, 1, 29, 2, and 4. And my D value of approximately 39. That's my new divisor. My old divisor was 37.3. My new one, 39. So one council member for every 39 people in each department. And that's how Hill-Huntington works. Good news is you guys will create a spreadsheet pretty soon to handle this one. This one's probably well, definitely the hardest to do by hand. Um, so, and you have to watch out for the cases where the quota has a point 0.4 in it. This one did not, but I just kind of made up the numbers. Um, but we'll have to be prepared for that. So we'll work on seeing that. But at least here, you get a chance to see how the process works on paper before you try to go put it in the big spreadsheet. Okay. I'm going to leave it here because it's been a lengthy video as it is, and hope that see you soon. Okay. And good news is this is the last apportionment. We use this one to the current day. No more after this. So hooray, we made it. Have a great night, everyone, and I'll see you guys soon.